Section 4.7, variable coefficient equations. Instead of having a second-order differential equation with constant coefficients, what if we have a second-order differential equation with variable coefficients? In section 4.2 and 4.3, we found solutions to homogeneous constant coefficient differential equations, homogeneous and constant coefficients A, B, and C. We found that all such solutions are combinations of exponentials, sinusoids, and polynomials. With variation of parameters in section 4.6, we extended this to non-homogeneous constant coefficient problems, yielding solutions valid over all intervals where f of t is continuous, ensuring that these integrals were continuous. As long as these integrals were continuous, we found a particular solution to the non-homogeneous constant coefficient problem. As we could hardly hope for more. Indeed, it is debatable what meaning this differential equation would have at a point where f of t was undefined or discontinuous. Yes, I suppose that would be debatable. Let's see what's next. Therefore, we move to the realm of equations with variable coefficients, where this and this are functions of t. The most we can expect is that there are solutions that are valid over only intervals where a sub 2, a sub 1, a sub naught, and f of t are all continuous. Fortunately, this expectation is fulfilled except for an important technical requirement, namely that the function a2 of t must also be non-zero over the interval. Except my thought is that if this were zero, it can be zero everywhere, but if it is non-zero somewhere, but zero at a single position, let's see the footnote. It says the whole nature of the equation, it reduces from second order to first order. It changes at the point of where a sub 2 is 0. So the problem is not having a constant coefficient of 0 here. The problem is having a coefficient that is a function of t which goes to 0 at some point. A relevant example I can think of is in the spring equation, where you put a mass here as part of your spring equation. What if that went to 0? What if you put a photon on your spring? You enter into an entirely different realm if you have a massless object. So since this thing is never 0, we can just divide it out. So a sub 1 over a sub 2 is p of t, and a sub naught over a sub 2 is q of t, and f of t over a sub 2 is g of t. And then they say there is a unique solution to this differential equation with 1 in the front. No, it's not an entirely unique solution. Look, it says for any choice of the initial values y sub naught and y sub 1, so the initial value of y and y prime, if you're given the initial position and velocity, basically, then there exists a unique solution on the same interval. So these problems are kind of like Euler's method. I mean, it's going to give you a closed form, but like Euler's method, which requires you to put in an initial value and just kind of follow it along, this one is also going to be sort of like that. It's going to give you, you're going to get a unique solution based on those inputs. I would think to get it as general as possible, you would go y of 0 equals y sub naught, and y prime of 0 is v sub naught, or something like that. V sub naught would be a good variable to use because it would represent some kind of velocity. Determine the largest interval for which Theorem 5 ensures the existence and uniqueness of a solution to the initial value problem. So in this one we're going to divide by t minus 3 and so get this t minus 3 gives you 1 here, over t minus 3 gives you 1 here, 1 over t minus 3 gives you 1 over t minus 3 here, and square root of t over t minus 3 gives you square root of t over t minus 3 there, and natural log of t over t minus 3 gives you this here. Now the domain of natural log t is greater than or equal to strictly greater than 0, and the domain of 1 over t minus 3 is t is not equal to 3. So the domain we could have, if we're using t equals 1 at the beginning, then the range on this is t0 is less than t is less than 3. So that's kind of an interesting idea behind if this is modeling something where t is equal to t represents time, then this formula is going to break down after like 3 seconds or 3 years or 3 minutes, whatever the unit on the time is. If this initial condition had been based on another value of time, like 4, then it would have been valid for all values of t from 3 to infinity, or all values of t greater than 3. Alright, Theorem 5, embracing existence and uniqueness for the variable coefficient case, is difficult to prove because we can't construct explicit solutions in the general case. So, for any choice of position and velocity, there exists a unique solution on the interval to the initial value problem. But if you let t sub naught and y sub naught and y sub 1 be just arbitrary values in the in that situation we can't construct an explicit solution. We'll have to see why. Let's look at this footnote. Oh, well, there's a chapter 13 apparently of the book that we are not aware of. It's the expanded text which does not appear in our book. Now we've been talking about the general case of p of t and q of t being coefficients to y prime. Now we're going to talk about a very specific case where the linear equation goes t squared y double prime plus ty plus y, or more specifically at squared plus bty plus c. This is going to be called the Cauchy Euler or equidimensional equation. And what do we have here? We have a t squared y double prime, t times y prime, and a constant term times y. And then we have just a t term next to the y is not a Cauchy Euler term because the coefficient before y double prime is not a constant times t squared. The nomenclature equidimensional comes about because if y has the dimensions of, say, meters, t has the dimensions of time, t would be in seconds squared, y double prime would be in meters per second squared, and then over here we've got just meters. This would be in seconds times meters per second. And so it's equidimensional because everything would cancel out. Let me just point out this use that immediately popped into mind when I was showing you that. Well, I'll first show you the use that I thought of, and then I'll show you why it doesn't work. Let's say I plugged in t squared was 1 foot squared plus, and then if I broke this down with 1 foot, 1 foot, 1 foot, and then say converted to inches, so it would be 144 inches here and 12 inches here, I realized that there's no t there, so that wouldn't be there. But then I realized that this is not going to help us in our problems, because this t squared here is a variable. If you want it to be accurate, you should not be putting feet and inches in your variables. Let me make this a rule that I might change my mind on, because there might be some situation where you have a very good reason to put units on your variables, but I just don't know what it is. Instead, where do you put your units on this? So if I have 3 feet, put it on your constant terms, and 11 feet and 3. Actually, what you would probably do is always put units in your variables, unless you have a good reason not to. But in any case, the 3 here would represent 3. Let's look for a second at a different version of this that just has the constant coefficients. And imagine what we would need to do to convert this from units of feet per second and feet per second squared to a problem where we had, say, feet per minute and feet per minute squared. So 3 feet is still 3 feet, but 11 feet per second is 60 times 11 feet per minute. And 3 feet per second squared is going to be 11 times 60 squared. So if we could create a unit, t sub unit equals 60 here, and so this would be 11 times t sub unit squared plus, I'm sorry, 3 times, this should have been 3 times t sub unit squared plus 11 times the unit time times dy dt plus 3 times y. Sorry, this was dy dt squared. So, but these unit times are constants. They would pop out in a similar way with the unit time and the unit time squared coming out. But in the Cauchy Euler equation, you have t popping out. You have t popping out as a variable, which is a different situation entirely. I'm not immediately coming up with an example where that would take place. But in any case, if we simplify this differential equation by dividing by t squared, we're going to get this. Would have 1 b over at and c over at squared times y double prime, y prime, and y equals f over at squared. Now this thing is going to have discontinuities at t equals 0, therefore we can expect solutions to be valid only for t greater than 0 or t less than 0. Discontinuities in f, of course, will impose further restrictions, so if we have discontinuities in that function. To solve a homogeneous Cauchy Euler equation for t greater than 0, we exploit the equidimensional feature by looking for solutions of the form y equals t to the r. If y equals t to the r, then y prime is going to be r times t to the r minus 1, and y double prime is going to be r times r minus 1 times t to the r minus 2. Let's rewrite this so that it looks a little bit more, so that the t to the r term stays rather than goes away, equals r times r minus 1 over t squared times t to the r. And then we can write this y prime, y double prime as t to the, well, let me just bring that t to the r over here, since t to the r is a factor of all three of them. And we'll have 1 r over t and r over t times, or r times r minus 1 over t. Now we're going to take that and multiply, yes, there was a t squared up here. If we multiply that by this, notice that 1 over t squared and at times t is t squared, and at squared times 1 is t squared. So I had best go ahead and multiply everything anyway, but r times r minus 1 over t squared is the first term, plus br over at squared plus c over at squared is going to have to come out to be 0 to get our homogeneous solution. And then if this is equal to some f of t over, what was it divided by? At squared, it's going to have to be f of t over at squared to get our particular solution. Let me try to write that in a more technically correct notation. It's more like finding and using the r that makes this thing 0 will produce the homogeneous solution. And if we can find an r that makes it equal to f of t at squared, that will produce the particular solution. Let's see, though, whether this leads to their characteristic equation for this system is going to be, I'm just going to multiply this by t squared, so I'll get r times r minus 1 plus br plus c equals 0. Whoops, this is b over a, this is c over a. And then multiply by a, we'll have ar squared minus ar plus br plus c equals 0, or ar squared plus b minus a times r plus c equals 0. So this thing is the characteristic equation, so it's going to have the roots r equals negative b minus a plus or minus square root of b minus a quantity squared minus 4 times a c all over 2a. So this brings us to our example 2, where we find two linearly independent solutions to the equation, to this equation. Notice that this doesn't have any, this isn't going to have any particular solution. It's going to have just the homogeneous solution. It just made me think how funny it is to say that a differential equation just doesn't have any particular solution. It sounds, well, it would be misleading to someone that didn't know the jargon. In any case, maybe it does have a particular solution. It just happens to be that the particular solution is 0. Seems like I've been developing two different ways of describing these problems, and they're not entirely that I should distinguish the different methods, because in one of the versions I've just been going starting with an equation of the form t to the r and then multiplying, finding the first derivative is r t to the r minus 1, r over t to the r, and the second derivative would be r times r minus 1 over t squared t to the r, which is equal to just this vector times t to the r. Now the characteristic equation, though, which is going to be produced by multiplying 3t squared, 11t, and -3 by this thing here is going to give, or when we set that equal to 0, it's going to give us two different values for r. And those two different values of r are going to be different parts of the solution, both of which will work. But when we put in the initial values, we'll end up with those C1 and C2. But I've also been doing another method where I do put in the C1 t to the r1 and C2 t to the r2, finding the first derivative of it is C1 C2 times, it's going to be the homogeneous derivative, or the derivative of the homogeneous equation is going to just basically pop out that r1 and r2. And then the second derivative is going to pop out the r1 minus 1 and the r2 minus 1. So it seems to me this version more accurately represents the full particular solution. And it might be especially helpful when trying to determine your constants of integration from the initial values. But in order to determine the form of the solution, it's more useful just to treat it this way, with just one of the values of r in there. In any case, we can go through this. 3t squared over t squared. First of all, this is supposed to be r squared minus r, not r squared minus 1. And then we can just go 3 times r squared minus r plus 11 times r minus 3 equals 0. So we'll have the 3r squared, and then 11r minus 3r is plus 8r, and then minus 3 equals 0. I want two numbers whose product is -9 and whose sum is +8. That suggests to me a 9 minus 1. So I can write that as 3 r squared plus 9 plus negative 9r plus negative 1r minus 3 equals 0, or 3r times r plus 3 minus 1 times r plus 3, or likewise 3r minus 1 times r plus 3 equals 0. And finally, we have r equals is either 1/3 or -3. So our homogeneous solution is going to be of the form C1 t to the 1/3 plus C2 t to the -3. So here you see the book has the same solutions, but what would happen if the two terms were equal or complex? If r1 and r2 are complex, they'll end up being complex conjugates of each other. So the real part can be factored out, and with a little bit of finagling of t being e to the natural log of t, and invoking Euler's formula, you can get it into the form this. Now here's something, I'm not sure if this is an error I've made somewhere, but it appears that there's no, they don't seem to, okay, it's this equality here isn't, let's see, this equality here is not strictly correct. He would, to get a true equality, he would need to involve both constants and convert it over to a using some kind of conversion of the C1s into the Q1 and Q2. And this is not supposed to be a plus sign but an equal sign. and then you'd have t to the alpha up here. But the main thing is, if these are real, then these are complex. But if these are complex, then these are going to be real. But there's a way of converting the complex roots, a particular set of complex roots of t to the alpha plus I beta and t to the alpha minus I beta into cosine beta and natural log t and sine beta and natural log t times t to the alpha. So the other thing is when the roots of 7 are equal. So what happens then? Then we're going to have y particular equals c1, c2, y1, y2 is equal to c1, c2 times t to the r and t to the r natural log of t. That makes me curious. If we set y equal t to the r natural log of t, what is y prime and y double prime? Well, the derivative of natural log of t, I believe, is 1 over t. And the derivative of t to the r is r times r over t t to the r. So this is going to be, y prime is going to be 1 over t to the r plus r over t to the r times natural log of t. Let's write that as a vector form of t to the r and t to the r natural log of t. We would have 1 over t times the one and r over t times the other. So that is y prime, and let's just call this y2 prime so that we can distinguish. This is the second part of the derivative. If we want to define the entire y, the homogeneous y, it's going to be equal to a constant times t to the r plus another constant times t to the r natural log t. And we can note that t to the r prime is going to be r times r over t times t to the r. So if I took y prime, it's going to be, we're still going to have our c1 and c2 in there. But then I'm going to put another matrix in between t to the r natural log of t, where c1 is associated with that t to the r, and we're going to have r over t times t to the r plus 0 t to the r natural log of t. But the derivative of c2 times t to the r natural log of t is going to produce this vector, 1 over t and r over t. Now we can pop out the second derivative by taking c1, c2 times the derivative of this, which is negative r over t squared, negative 1 over t squared, 0, and negative r over t squared, times t to the r natural log of t, plus, I'm just going to take c1, c2 again. Actually, let's just, in fact, instead of doing that, let's just put this whole thing in brackets, and then take the derivative of this, which is just, we're just going to pop out another thing that looks exactly like that. So r over t, 1 over t, r over t, 0 squared times t to the r natural log of t. Now let's go ahead and do the square of this thing. It's going to be r1 r0 times 1 over t squared, and then this is squared, so it'll be r0 1r. So that's equal to 1 over t squared times, it'll be r squared. We'll still have a 0 over here. I'll have a 2r down here and a single r down here. So now that I have squared this term and it gives me that, let's separate this out so that, as a matter of fact, this has a 1 over t squared in it too. So let's just bring that out of there, and we'll have a bracket with this is negative r 1 negative r 0 plus that times what's out here, t to the r natural log of t, and we'll still have our c1 and c2 in here. And our final form, it shouldn't be equal, should it? It should be c1 c2 times, and we'll have y double prime equals this. We can simplify it a little bit more. Y double prime equals c1 c2. I can actually multiply this through over to there, so this will be t to the r minus 2 and t to the r minus 2 natural log of t. I shouldn't even do that. I should just put it as 1 and natural log of t times 1 over t squared t to the r. And then this part can be summed together. R squared minus r, 0, 1 plus 2r, and r minus r is 0. And this is not supposed to be a divide. It is just supposed to be natural log t. Which means when you do this, by the time you've done the second derivative, if I've done this right, the natural log t terms have canceled out completely. So we have essentially verified this by direct substitution into the differential equation. No, we're not entirely done yet. We would need to actually make a linear combination of y double prime, y prime, and y. Let's see, to prevent confusion, let's change these constants to q1, q2, and then we'll need to write a vector of y, y prime, y double prime times these coefficients, where y is just going to be q1, q2 times t to the r natural log t. Y prime is going to be, well, we'll have q1r over t, because this and this, and then this will be q2 over t. It'll be, I won't fit here, but it'll be q1 over t plus q2 over q2 times r over t. And then in the final place, we would put q1 times r squared minus r plus q2 over times 1 plus 2r, and this would be 0, and then this part would be q1 times 0 plus q2 times 0 would be 0. And then you'd want to multiply a, b minus a, and c by both sides of this. So basically it'll be that. Whoops, I goofed. I put this on the wrong side. Over on the other side, we'll have, this should be q1 r over t plus q2 over t. And then up here at the top row, it's q1, let me write it in black, q1 times r squared minus r plus q2 times 1 plus 2r. And there's one other mistake that I have in here. The t should have been removed out of this. Or more likely, the t squared should have stayed in this. One of those is true. I believe it's the t squared should have stayed, so that this side is the same. And then this whole thing would be over t squared. If this thing is correct, though, all of your q1 terms should cancel out, and all of your q2 terms should cancel out once you multiply it by a and b minus a and c. And since it's a double root, you'll be able to use that. What's the ordinary equation? R equals negative b over 2a is the way it would be in a regular quadratic equation. So 2ar plus b would be 0. In this version, we're going to have r equals negative b minus a over 2a, which would be a minus b over 2a, which would be 2ar minus b, 2ar plus b minus a equals 0. So how else could I say that? Factor out the a's. A times 1 minus 2r plus b equals 0. I guess I factored out a negative a. But that would mean that something like the 1 minus 2r here is equal to negative b over a. Actually, positive b over a. Anyway, I'm not immediately seeing how to resolve that this thing is equal to 0. But what I'm trying to do is to establish kind of a general method by which you would if you needed to, which you probably won't. Not in any of the problems that we have in this book.